Hi everyone, so we're going to do the last lab exercise, or I'm going to do it and you're going to do it. We'll see how it goes. This is going to be really awkward because, uh, you know, normally you would build these models. I've got them built, I'm going to show them to you, but there's still a lot of it that, you know, I want you to do in terms of drawing Lewis structures and figuring out the geometries and learning that material. So, um, and then I don't know in terms of flipping the camera down to look at the page versus what I'm trying to show you as well. You know how awkward that is. I really need two webcams to do this, and then some decent video editing software so I can splice it all together. But we have what we have, right? So we'll just go with it. And I guess the most important thing, as always, is if anything doesn't make sense, please post a question to the discussion page. This of course is a lab everyone needs to get 100% on. And I do know that, you can do it just, especially the way I programmed it in WebAssign. You can just click on it like a very boring video game, like that one commercial, or what, I can't remember what one it is, or anyway. Um, you know, but you won't learn anything by doing that. If it's a pull down menu, multiple choice, and I do see students doing this on other homework and things, and I understand that you want to get the homework points, but it's really important that you learn this material and understand how to get the geometry from the Lewis structure and how to draw the Lewis structures. So let me know if you have, there really ought to be a lot more questions on those discussion pages. um, anyway, so let's see how this works. And big picture, I want you to understand the concepts behind this and also be able to do it. So first of all, what is VSEPR, as we say it, VSEPR? Well, it stands for valence shell. I would normally write this out, important to talk about, right? But it's all written in here very carefully so you can read it as well. But it stands for valence shell electron pair repulsion, and I go by electron groups rather than electron pairs, as we talked about with hybridization, because a double bond or a triple bond counts as one group in terms of how it works. But it's based on an incredibly simple idea. The simple idea is that electron groups, they're negatively charged, and they're going to repel one another and get as far apart as possible from each other. Orbitals take up space, and they're going to repel one another, and the geometries that you get from that really simple idea, in fact, doing with, as we're going to do with the balloons in the first exercise, the geometries that you get are very good geometries. And if you read the lab handout, which of course I hope you do, the number of 103, this was as of 2015 last time I checked, 103 million unique chemical compounds. uh, Most of those are organic molecules, and the hybrid orbital model and the VSEPR geometries that you get from that will predict the geometries of the vast majority of those. So that's incredible. Just the idea that you can demonstrate with balloons these geometries, can predict those structures is amazing to me. And then I talked about why molecular shape is, or I can't remember which one you're going to watch first, but and I may repeat myself somewhat, but the one from class where I kind of reviewed it all in the table, um, I did that one first, but really this is the one you should probably watch first. Uh, the idea, why we're interested in molecular shapes, I kind of went through that in that one, so I won't do that again. But just quick example, the fact that a water molecule is bent, ends up meaning it's highly polar, and it can do hydrogen bonding, and so it has a really high boiling point compared to other molecules of its size, same size, and those properties then we can predict. Normally, I would say the first thing we do in Chem 114 is we use those kind of things to predict properties of molecules based on their shape. And we're not doing that this year because we skipped a chapter. We'll start with that other one most likely. But anyway, it's really important. And you know biochemical reactions, enzyme reactions, and things that lock and key kind of models. So the shapes of molecules are really important. I've got my little notes of what I'm supposed to say over here, right? Okay, so here's what we're going to do. I'm going to do you know, make sure you do read this and that you can recognize those ways of drawing a molecule and what they represent. I'm going to do the balloon part of it first. And so the first exercise is just using balloons to represent orbitals. And so if you can flip to, if you would, go ahead and flip to page 3. So you've got this in front of you. You're going to fill it out as I go, hopefully. And, you know, I'd like to be showing both if I, you know, had the technology. Don't worry about the drawings. You know, that you're not going to, for the drawing the shapes of the balloons, we're not going to do that part of it in WebAssign. But the idea then is just using balloons. And I love the balloons part of it. This is my favorite part, and actually probably the most important part in terms of learning the concepts of VSEPR, of molecular geometries. Just the idea that you can use, you know, a balloon to represent an orbital. These electrons take up space, and that's going to predict the geometries is just kind of amazing to me. So the way this works, you know, we start with two groups, two balloons tied together. And so this represents, right where they're tied together would be the central atom. And these are the two orbitals connected to that central atom. And you just kind of look at them and see what's the shape there. If they're as far apart as possible, what would that be, right? Well, the balloons, the ends of the balloons and that central atom, they would be in the same plane, right? And to get as far apart as possible, it'd be in a straight line, 180 degrees. And so then that geometry would be linear, okay? Now, what if we stick a third balloon in there and look at it? And hopefully you can see this. So where they connect is the central atom, and then you've got 3 orbitals connected to that, and it's a triangle, right? The tip of these is a triangle, and to get as far apart as possible from each other, they're going to all be in the same plane, and so we call that trigonal planar, and that's in fact what you have. So that would be our sp2, right? 3 things around the central atom is sp2 hybridized, and the balloons predict the electron geometry really well, and the bond angle then as well. Okay, what about 4 things? 4 balloons. So 2 sets of 2, and you can do, oh, you gotta be kidding me. That's embarrassing. But you know, I can't redo it, right? I gotta just do this. So we are gonna just bear with me as I tie the balloons back together. Okay, so tying 2 together is I'm just gonna twist it as best I can, and we'll call it good. All right. Hopefully they'll stay together long enough for this. Okay, I'm a little punchy. So we're gonna stick these together, and you might think, well, maybe they look like that. Maybe they're all flattened in the same plane. But I want to make sure they're going to stay together first. So let me twist them together. I'm not sure they're going to stay together. That's the actual geometry. And we did that the other day, right? We looked at the tetrahedral. 4 things, sp3 hybridized. The balloons predict the geometry. And in fact, molecules are always bouncing around, right? Colliding with one another. We learned about that in the ideal gas chapter. So let's say you thought they were in a plane like that. Well, as they're colliding, you just tap it and a little too close, and they adopt that geometry. So the balloons representing the orbitals around that central atom will adopt the correct molecular geometry and the correct electron geometry. So that's kind of cool. Now, I don't know how well this is going to work. Let's just see. See how quickly I can do it or not. So I just want to make sure that everyone then has this. Okay, so forget about the shapes, right? We don't have to draw that. Are the balloons planar when they had two? Yeah, they were. So yes. The approximate bond angle, two things as far apart as possible, was 180 degrees, because there's 360 degrees. So that's opposite sides of it, right? I mean, I can draw it. That would be what the molecule would look like. But if you just draw the balloons, it looks like that, right? And then the geometry then is going to be linear. They're in a straight line as far apart as possible. Okay, and like I said, I believe I have these programs that this is just a pull down menu for these. So you could just click till you get it right. But please make sure you understand it. I understand that temptation to just get it done, like I've seen people do on the homework, but you want to learn and understand and remember it. And then, so three things that was also planar, the balloons were, and 120 degrees. And the geometry then was a triangle, but we have to make it fancy just, to make it, instead of just saying a triangle, we'll call it trigonal. And since they're in the same plane, it's trigonal planar, okay? And then four things, are they planar? No, they're not planar, right? It's that tetrahedral geometry. We've got the central atom. Anyway, and then the bond angle, 109.5 degrees. Which we can't really tell very easily from the balloons, excuse me, but then geometry is tetrahedral, yeah. All right, so now the next exercise, and maybe I'll just leave this down here like this. The next exercise is, we'll see if that works, building these models, okay? And there's a lot in here about how to build them. Don't worry about that, right? You don't have the model kits. I'm going to build them. So this is the table. And the idea with building them is to try and help you understand. I think I need it more like that when I actually put the models in there. Maybe that's going to look a little weird. But all right. We'll see how it works. Okay, so the idea with the, I think I lost my train of thought. The idea with the model kit is actually to help you picture things, and it's unfortunate you can't build these, because I do think it helps. And the way these work, they're really kind of cool because they have the hybridization written on them, and so that will give you the correct bond angles. But we can't do that. So what you're going to have to do, excuse me, you've got to draw these Lewis structures, right? So you're in WebAssign, you'll have to draw the Lewis structure, and based on that Lewis structure, answer these questions. How many lone pairs? So I'm not going to do that. You'll have to do it. And then number of atoms bonded, so you'll do that. Total number of electron groups, well, it's just how many lone pairs plus number, so it's just this plus that equals that. And then based on that, the geometry of the electron pairs comes directly from that hybridization, right? So the total number of electron groups will tell you the geometry of the electron pairs, and then the geometry of the molecule, and then the bond angle. So let's look at these models together and see, and don't, again, you don't have to worry about the how to draw the wedge structures. You need to be able to recognize those wedge structures. Let me see if I can flip back one so you would show you what I mean. Just, that's what the wedge structures look like, and they just show how they're connected. It's like a extra good three-dimensional representation of a Lewis structure, so that the wedge is coming out at you and the dash is going behind and the solid lines are all in the plane of the paper. Anyway, so you've got to do the Lewis structure part of this and identifying the geometry from that. But I've built the models to help you with the geometry and the angles. The idea is that we're going to measure these angles. Well, this is carbon tetrachloride. Okay, so the first one, where you've got a carbon in the center and 4 chlorines, and of course this is very similar to the CH4 that we did in the hybridization, right? Because you got 4 atoms on this central carbon, and so you see what it is, and you already know it's tetrahedral, right? I'm not giving anything away, and just I don't want to give you all the answers. I do want you to go through it, but it's kind of this table is meant to show the difference between geometry of the electron pairs and the geometry of the molecule. So understanding how those are different, that's what we're trying to do here. And so this is the CCl4 molecule. And the idea would be you could stick it on the compass protractor. You know what? I never get that right the first time. Anyway, and you can measure the bond angle with it, and you can see then if I get it lined up just perfect, which is hard to do, it's going to be right at that 109.5. I don't know if you can see that or not, as long as you choose the one that say sp3 hybridized on there. All right, so that's what that, hopefully that helps you picture that tetrahedral geometry. But then the whole point of this one, so you down here you have to answer what hybridization is. Hopefully you know that. And the whole really star this question, right? This is the point of this first table, this exercise. What's the difference between electron pair geometry and geometry of the molecule? And so I want to show you, this is the ammonia, and I did talk about this in the other one as well. This is the ammonia molecule, where so you've got nitrogen in the center and then our 3 hydrogens. And I'm just going to do it because I don't want there to be any confusion. But you can see these have the same electron geometry, right? They're identical in electron geometry. It's the tetrahedral. And then when you get to naming the molecular geometry, well, this one has atoms on all the orbitals. And so the molecular geometry and the electron geometry are the same, but ammonia has a lone pair. And when you name the geometry of the molecule, we're just interested in where the atoms are. So you can kind of cover up this lone pair and say, well, what's that geometry? And it turns out, it's triangle. And then this atom, the nitrogen, is above the plane of the board or of the paper. And so that makes it a pyramid. So it's trigonal pyramidal there. And so that's the difference. Make sure you understand the difference between molecular geometry and electron geometry. And I built water as well, so you can see what water looks like. It gives away the Lewis structure, helps you with the Lewis structure. I don't think you'd have trouble with the Lewis structure of water anyway, but oxygen, 2 hydrogens, 2 lone pairs there. Okay. All right. So bond angles, answer all of those questions. Should be good. this question here. Talked about this in the other one in terms of, you know, the bond angle starts out the same, but then if you have this lone pair here, the lone pair is a little bigger than the bonding pairs are because it's not constrained by the bond axis, you know, of having a nucleus out here. And so they're just a little bit bigger, and it's going to push these orbitals down a little to make that bond angle a little bit smaller. Okay, so hopefully you can understand that and answer that question. All right, and then so that's the purpose of this. I know I'm repeating myself, but I want to make sure there's no confusion. The difference between the geometry of electron pairs and the geometry of the molecule, and it's in fact the same sequence of examples that's in the class notes, I guess you would call it now. All right, so then what about this next exercise? So the next exercise is going through and change, well, I'm going to give it away, right? Because normally you'd have to build these, and you'll have to enter the Lewis structures or draw the Lewis structures, but we've got carbon with 3 hydrogens on it, the carbon with 2, and then just 1, and it ends up being, I'll just write it in here even though you're going to have to fill this in, the effect of single, double, and triple bonds on the hybridization and geometry. Okay, so that's what we're figuring out in this exercise. If you change that geometry from having a carbon-carbon single bond, which is represented here, hopefully you can see that okay. So carbon-carbon, the 3 hydrogens on it, and that's what that first, the ethane, that's what that looks like in terms of the model. And you know, when you measure the bond angles on this, it's going to be the 110. I don't know if you can see that again, because this has got 4 things around it. This carbon's got 4 things around it, so it's sp3 hybridized. Okay. Now, if you go to the next one, the ethene, this is what how a double bond is represented with this fairly inexpensive, okay, cheap model kit, but it's good because it's the sp2. There's 3 things. So if this is a carbon, there's 3 things around it, so it's sp2 hybridized, right? And I use the ones that say sp2 on them. So then when I mean, you can look at it and see what that angle's going to be, right? I'll stick it on that atom, and lo and behold, it's right at 120. I don't know if you can see that or not. Okay? And so as you go through and fill this out, hopefully having seen these will help. This is what the triple bond, this last one, acetylene, looks like. And you know, again, it's kind of goofy. They're not, these are the fairly inexpensive ones. So here's a carbon here, and this would represent a carbon here. This is a carbon to hydrogen bond. This is carbon to hydrogen bond. And this is supposed to be a triple bond, represent a triple bond there. So does that make sense? And you can see what the geometry is, right? And you can see what the bond angle is as well without even measuring it. All right, so you'll go through and complete this table again. And so in this lab exercise, these 2 tables represent all the options. Okay, if we're going up to sp3 hybridized, you know, and this table, I know I'm giving this all away, but sp3 hybridized for all of them, and the different possible geometries that you can get, which is the same as that summary table then that I did for the class. And then this is the effect of changing the hybridization, okay? Staying under 4 groups always. So like I said in the other one, we're not going to do anything but the base geometries for 5 or 6 groups around the central atom. So that's the possibilities. And then what's the last thing that we have to do in here? Let me just make sure I'm doing it correctly. Exercise 3. So bring that down. All right. So exercise 3. So the rest of this hopefully helps you understand VSEPR and molecular geometries and using the hybrid orbital model to get the, and we just have to be familiar with it, right? In terms of knowing the bond angles, what the hybridization is, what the electron geometry is, what the molecular geometry is, and that summary table that I did in the class notes. What else do we have to be able to do with it? Well, so the big thing on the study guide, which, oh shoot, I had it right here, but I don't. On the study guide for the chapter is if you're given a Lewis structure, can you take a Lewis structure and determine the geometry? And so we'll have to take a Lewis structure and determine electron geometry or molecular geometry or the bond angles. And so that exercise 3 just goes through and has you do a few Lewis structures and get the molecular geometries from them. And again, I know you can just, once you have the Lewis structure, you can just do a pull down and find it. But also, when you look at this, I'm going to help you out here because I know this is one of those, when we do it, when we're together, there's a lot of questions about. So this, we're just looking at the geometry of this one carbon. And let me get that focused for us. And so this, we really need the backbone for Gen Chem of how this goes together. So I tried to describe it in words. Determine the geometry around just that underlying carbon. This condensed structure indicates that this carbon atom is bonding to the 2 other carbon atoms and the oxygen. And so this always causes a lot of confusion in lab when we do it in lab. So let me just draw what we mean by that. So the carbon is connected to the 2 other carbons and connected to the oxygen. So that's our starting point for the Lewis structure. And then you just have to fill it in. I'll help even more because these hydrogens, remember, hydrogens are terminal in a molecule. They can only form that single bond. So when we stick them on there, they just fill out that carbon, and carbon's octet is now full. So you really just have to draw and figure out this central part of it to complete the Lewis structure. And then we're only interested in the geometry around this carbon. Okay, I mean, we could do it around the other ones too, but that's the one it's asking for. And I think, yeah, so same thing with these. Should I give you the backbones for those as well? Might as well. Okay, let's go ahead and do it. I'll just draw them on here. And let's see if I've done it correctly if we read it. Of course, I know that I have done it correctly. This is a very popular molecule on college campuses. Don't tell anyone I said that. So this condensed structure indicates that the carbon atom is bonded to the other carbon atom, 2 hydrogen atoms, and the oxygen. So I got it right. And then this is one of my favorite molecules because who doesn't like pickles? We made refrigerator pickles last summer, not this last summer, but summer before with my kids. This summer our cucumbers just went kaput. But it's too dang hot and dry. Anyway, so this is that structure. Okay, so this is vinegar, acetic acid. And so you can fill out the rest of the Lewis structure from that. And then you're just determining again on these, just the one that they're indicating. So that carbon and that carbon, what the geometry is for it. All right, so I don't think that I've forgotten anything in doing this lab. I sure hope I haven't. Uh, the balloons, I think, is important because that's, so what do we need to know about um, VSEPR, right? The concept, just the idea that we can use the repulsion of these electron groups to predict the geometries of millions of molecules. That's unbelievable, right? Based on the same principle as tying balloons together, and it works. Um, and then being able to know, the summary stuff that is in the class handout that I did, and then being able to um, so those two tables and all the different possibilities there, and then given the molecule, write the Lewis structure, or given the Lewis structure, come up with the geometry. All right, thanks. Please, if you need any help with this, I know nobody's going to need any help with this because you can click and get the answer, because I give you multiple submissions. So you're not going to need any help getting the points on the lab. But please, if you don't understand some of it, any of it, please post to the discussion page and have a conversation, and I'll help you understand it, because you got to be able to do it on the test on Friday, Saturday, Monday, or Tuesday, whichever day you're taking the test. All right, thanks everyone.